welcome back to our study of differential calculus when we are using derivatives in order to find optimal solutions to problems. Here's a particular problem I have written in front of you. We're in section 4.7 now, but I used to work in the high volume cell phone industry, and it's interesting when you're making things like you say here, Pepsi Cola makes 30 million cans of pop per month. When you put out 30 million chips a month, you know, if you can figure out a way to save 5 cents, you can be a hero for your company and certainly pay for your salary. So you pay attention to little things. And so when you're trying to find the best way of doing things, as you would when you're optimizing, again, it's a pretty interesting problem. So here we go. We've got Pepsi Cola makes 30 million cans of pop per month. Each cylindrical can, so you've seen one of these cans, is a fixed volume. So we're going to say it's 12 ounces. A fixed volume. What cylindrical can dimensions should be used to minimize the amount of aluminum required to make the can? So the amount of aluminum required to make the can would be the surface area. We're going to ignore any cost differences between the sides and the tops. And we're just going to go with straight kind of the surface area. We want to keep the volume fixed, but we want to minimize the surface area of the aluminum. Okay, so where do we start? Well, as we start with any problem, you want to draw a picture. So that's what I'm going to use this to illustrate kind of a thinking process. I want to draw a picture. Okay, I guess I could just say that, and I'll try to draw a can here, but you know, here's my can, and I've got, oops, I've got a top on top also. And you know, the can has a what? Well, it has a radius to it. It has a radius. So how skinny is the can, and how tall is the can? This might be how tall the can might be, h. So these dimensions, the height of the can and how wide the can is by the radius, really determine the dimensions. Next thing I'm going to do is I'm going to write down the equations. Well, I know my volume. What's my volume of this can? So the volume is equal to what? Well, it's going to be the base area, which would be what? Which would be pi r squared. Pi r squared times h, and that's going to be fixed, right? This is going to be a fixed constant. And this thing we said, you know, i.e. 12 ounces. Okay, and then, well, what's the other thing? Well, I have my surface area. That's the amount of aluminum I need. Surface area would be what? Well, if I cut the can and unroll it, right, I got the sides of the can are going to be, it's going to be height. I probably didn't draw this very well, but this would be 2 pi r plus, I got the top and the bottom, which is going to be 2 times pi r squared. So what is this again? The area, surface area, that's an r down here, by the way. It's going to be 2 pi r h, 2 pi r h plus 2 pi r squared. That's going to be my surface area. Okay. Now notice I'm trying to minimize. I want to minimize. Whoops. I want to minimize SA, but the surface area is, if you look at it, it looks like it's a function of 2 variables, r and h. If I'm going to minimize, this is where our applications of the derivative comes in. I want to take the derivative, set it equal to 0, and I want to guarantee it is a minimum and not a maximum. But I can't work with 2 variables. I need 1 variable. But notice I have two equations, so let's see what we can do here. I now know what? It's 2 pi. So I'm going to rewrite this 2 pi r squared plus 2 pi r. Well, h. What's h going to be? Well, look up here. If I bring this down, I could see v over pi, v over pi r squared is equal to h. So I now know what is v? V is a constant. V is not going to change. It's a constant. All right, so there I go. I want to clean that up a bit. Let's clean up this equation. And now I'll say surface area as a function of r is going to be, it looks like I can pull a 2 pi out even. I might even pull the 2 pi. 2 pi out front, and I've got an r squared plus, look at this. This is going to show you this. I can cross that out, make that a 1 plus 1 over pi r. Okay? Pi over r. Did I do that right? I brought out a 2 pi. So I got pi r. Oh, I got a v on top, of course. Jeez. Okay. V over pi r. So now I've got my equation. I've done the hard part. That to me is the hard part of the problem. I've got now a function of r. I could plot this on my calculator. I guess I could put in a constant v, and you'd get a function that will hit some kind of minimum. And what you want to do is that's the can you want to build, the minimum surface area, the minimum cost can. Okay, so what do we do now? Well, now we do the calculus. 4, so 3, we got the equations, I guess. This is really 3 maybe. 3, I got to a function of a single variable. 4, I'd say do calc. Do calculus, so I'm going to say, well, what is ds dr equal to? Well, it's going to be 2 pi times 2r. Oh, my penmanship is terrible. 2r minus what? V over pi r squared. Okay, verify that derivative there, right? What's the derivative is really v pi r to the minus 1. So I'm going to take, with respect to r, I bring them negative out front. I get r to the minus 2, which is that. Okay? I want to set that equal to 0. What am I going to get? Well, I'm going to get, it looks like, if this is going to be 0, the inside has to equal 0. So we're going to get 2r is equal to the volume over pi r squared. Doing a little more work over here, I would get what? I get r cubed has to be equal to v over 2 pi. And then what's r equal to? Well, r is equal to the cube root of v over 2 pi. If I know what r is, apparently I know what h is too. But the first thing what I might want to do, I want to minimize, I want to make sure, did I find a minimum? Was this a minimum? Okay, was this a minimum? I'm still How do I find out if it's a minimum? Well, I could apply a second derivative. I could say, what is ds? ds squared dr. I look at a second derivative of this, and what do I get? I'm going to get 2 pi. I go on the inside here and I get 2 plus 2v pi r cubed. Okay, 2 pi r cubed. Is that going to be positive or negative? Well, you know, that's positive, positive. The volume's positive. R cubed is what? Well, r cubed is just v over 2 pi. So this certainly, I can actually equal, this is equal to 2 pi. At this point here, it's going to be 2 plus 2v over pi. What's r cubed equal to? R cubed is equal to that. V over 2 pi. This actually gets pretty clean. I know it looks a little messy. Looks 4 pi. It looks like the whole thing is going to become, this is going to be 4. These are going to cancel. 4, 6 is going to be 12 pi. 12 pi is greater than 0, right? So remember, what do I have? I have a positive derivative, so I've got a minimum. That is a minimum, no doubt about it. Okay, so I've got my spot. I've got my answer here. I'm about ready to I got this thing in the bag. I'm feeling good. I've done all the work. It's looking right. Now, the next thing I got to make sure I do, I got to answer questions. And I answer the question asked. See how this thing looked. Okay, what cylindrical can dimensions should be used? I want to know the dimensions. Okay, well, I've got one of the dimensions. I just want to know the dimensions, so I know r is equal to the cube root of v over 2 pi. What's h equal to, though? H is equal to v over pi r squared. I'm going back up here now, right? Pi r squared. So it's a little bit, this is in general. We're getting problems in general here. Come on, move over now. Nope. Move this guy over. All right, so H then is equal to V over pi. And in order to take r squared, you could write it like this. It could be the cube root of v over 2 pi squared. That's a way to write it like that, okay? Okay, so you would say that there's your dimensions. Now, if you wanted to get real numbers, you could plug in your volume in ounces and make some calculations. You probably want to go to milliliters and make the R and H centimeters. Okay, so what do? We did a calculus problem, and I just wanted, the process is really the thing. Draw a picture. Get a good picture so you know what you're doing. Okay, write down the equation, step 2. When you get equations, a lot of times you might get an equation of 2 variables. You need to reduce that to an equation of 1 variable, okay? And this is the hard problem. 1, 2, and 3 are the hard parts of this. After that, you do the calculus. Once you have a function of the variable, you minimize or maximize that function. Do the calculus, set the derivative equal to 0, check that it's either a minimum or maximum. Then, don't forget, this happens all the time in a test. Go back and answer the question. Okay, make sure you've got the answer in front of you. Read it again and give it in the proper form. Okay, these are interesting problems. I hope you enjoy your homework, and we'll see you soon. Bye-bye.